Hi everybody, good evening, how are you? Thank you for tuning in to my channel. So, every video probably needs some kind of introduction. This video today will be about interrupts in the PIC-18 microcontroller family, the 18F. And there is a popular manual for the 18 series family, and it's actually called the PIC-18C MCU Family Reference Manual. If you look in the video description below, I will have left a link for that. That is what I'm going to be covering. That reference manual came out a long time ago, in the early 2000s. It is almost 1,000 pages. So I have covered material out of that before. I have a PIC programming playlist on my channel, which is mostly just memoranda for me. Some of these videos are publicly viewable. Many are not, especially where I risk plagiarizing. So here, around the 160 video count mark, you can see I've created other similar videos on the program counter, the stack, I/O ports, file select register, status register, etc. Anyway, I'm not an expert on this, and these videos I create are generally for me, but I make them available because who doesn't want to be popular on YouTube? So today's video is about interrupts. And why is this video worth watching? Well, if you don't like reading a 1,000-page manual and you'd prefer to hear it, well, maybe that's going to be helpful to you. And it's going to be helpful to you if you'd like to learn about interrupts. Now, it won't be specific to any particular 18F PIC chip, but it will be a general overview. And I'm not being very creative. I'm generally just going to read the manual as it's written. Thank you for listening. Alright, here we go. I have the reference manual opened up. I have my browser search, and I can search for things like the word interrupt. When I do search for that, I get 1,400 different examples, so that's not that helpful. How do I cover all that? But anyway, the table of contents says that interrupts are section 10 of the manual. I'm currently on page 5. If I click this, I believe it takes me to section 10. I'll read this. Introduction, control registers, interrupt handling operation, initialization, design tips, related application notes. I found it's usually just blank. Revision history. Okay, I'll click on it. It takes me to page 175. Once again, this manual can be found in the description below. There will be a link, and if you'd prefer to read it yourself, check out page 175 of the PDF. Well, I just read that, so won't read it again. Okay. Introduction. Interrupts can come from many sources. These sources currently include external interrupt from the INT, INT1, and INT2 pins. Change on RB7, RB4 pins. Timer 0 overflow, timer 1 overflow, timer 2 overflow, timer 3 overflow. USART interrupts, receive buffer full, transmit buffer empty, SSP interrupt, SSP I2C bus collision interrupt AD conversion complete. So that's analog to digital. Here's the capture and compare interrupt, LVD interrupt, parallel slave port, CAN interrupts, receive buffer 1 full, receive buffer 2 full, receive invalid, transmit buffer 0 empty, transmit buffer 1 empty, transmit buffer 2 empty, bus wake up, bus invalid error. As other peripheral modules are developed, they will have interrupt sources. These sources will map into the 10 registers used in the control and status of interrupts. These registers are INTCON, INTCON 1, INTCON 2, INTCON 3, PIR 1, 2, PI 1, delicious, PI 2, even better, IPR 1, IPR 2. The INTCON register contains the GIE/GIEH bit. This is the global interrupt enable bit. When this bit is set, all interrupts are enabled. If needed for any single device, additional INTCON, PIR, PIE, and IPR registers will be defined. Next page. Interrupt priority. There are two interrupt vectors. One interrupt vector is for high priority interrupts and is located at address 000008H. The other interrupt vector is for low priority interrupts and is located at address 000018H. When a valid interrupt occurs, program execution vectors to one of these interrupt vector addresses and the corresponding global interrupt enable bit, GIE, GIEH, or GIEL, is automatically cleared. In the interrupt service routine, the sources of the interrupt can be determined by testing the interrupt flag bits. The interrupt flag bits must be cleared before re-enabling interrupts to avoid infinite interrupt requests. Most flag bits are required to be cleared by the application software. There are some flag bits that are automatically cleared by the hardware. When an interrupt condition is met, that individual interrupt flag bit will be set regardless of the status of its corresponding mask bit. For external interrupt events, such as the RB0, INT0 pin, or port B change interrupt, the interrupt latency will be 3 or 4 instruction cycles. The exact latency depends when the interrupt event occurs. The interrupt latency is the same for 1 or 2 cycle instructions. The return from interrupt instruction, retfee, can be used to mark the end of the interrupt service routine. When this instruction is executed, the stack is popped and the GIE bit is set to re-enable interrupts. Here is figure 10.1, interrupt logic high level block diagram. And I didn't quite capture all of it on the screen. I will just read through things that are intelligible, like close to being sentences. So, yeah, here's the TOIF, RBIF, RBIE, int0f, int1, and related bit registers, would we call that? Wake up if in sleep mode, interrupt to CPU, vector to location 0008H, high priority interrupt vector address, peripheral interrupt enable bit, peripheral, that's what PI stands for, peripheral interrupt flag bit, peripheral interrupt priority bit, additional peripheral interrupts, IPEN, GEIL, PEIE, IPEN, high priority interrupt initialized, disable low priority interrupts. And here's some dashed line. High priority interrupt generation points in this direction. Low priority interrupt generation points to everything below this line. Peripheral interrupt enable bit, peripheral interrupt flag bit, peripheral interrupt priority bit, additional peripheral interrupts. Wake up if in sleep mode, interrupt to CPU, vector to location 0018H, low priority interrupt vector address. So, sorry to bounce around, but I just scrolled back up here. I'm going to read this very first two sentences again. There are two interrupt vectors. One interrupt vector is for high priority interrupts and is located at address 0s and 8H. The other interrupt vector is for low priority interrupts and is located at address 18H. So that's, I read that because that's kind of what this interrupt logic high level block diagram is showing. It's showing the interrupt to CPU vector to this location and also to this location. So low priority interrupts, I guess, is categorized like this, and it's going to send the vector to this location, and high priority interrupt stuff is on this side of the dashed line, and it sends the interrupt to CPU vector to location bunch of zeros 8H as a high priority. Well, anyway, continuing on, so I covered the interrupt logic high level block diagram, and the next diagram is high priority interrupt logic block diagram. Okay, so once again, the previous chart broke things down into high priority and low priority. So this chart here, for just the high priority interrupt logic block diagram, does it mimic what is shown above? I'm a bit of a caveman when it comes to understanding technical stuff. So I just surmise that a lot of different bits can trigger a single high priority interrupt. A lot of different things. I won't read this chart. It's be confusing, I think. Not confusing, but I'm not going to read all these alphabets. It'd be like alphabet soup. But anyway, interrupt to CPU, vector to location 000008H for the high priority interrupt logic block diagram. Scrolling down, I bet you it's the low priority one. Good guess. Low priority interrupt logic block diagram. Are these same, I don't know, registers? What do you call those? Bits? Are they the same ones that appear above. Like, for example, we have timer 1 IF, timer 1 IE, timer 1 1P. I scroll down to the low priority, timer 0 IF, timer 0 IE. Okay, well, here's a better example. Timer 3 IF, timer 3 IE, timer 3 IP, timer 3 IF, timer 3 IE, timer 3 IP. So some of the different timers seem to be like an AND gate or whatever type of gate this is in the low priority and also the high priority. So these bits aren't necessarily designated for high or low priority, it would seem. The capture and compare is in the other chart too. Forgive me if you know better. I'm actually learning this as I read it. I'm not going to say I even understand much of it. Anyway, and even watching this video like 3 or 4 times later, I still may not completely understand what this stuff says. It's like mumbo jumbo to me. Anyway, 10.2, page 180, control registers. Generally, devices have a minimum of 4 registers associated with interrupts. The INTCON register contains the global interrupt enable bit, GIE, as well as the peripheral interrupt enable bit, PEIE, the PIE/PIR register pair that enables the peripheral interrupts and displays the interrupt flag status, and the interrupt priority register, IPR, that controls whether the interrupt source is a high priority or low priority interrupt. Okay, moving down to page 181. INTCON Register. The INTCON registers are readable and writable registers that contain various enable priority and flag bits. Register 10.1 INTCON Register, GIE, GIEH, PEIE, GIEL, TMR01 or TMR0IE, INTOIE, RBIE, TMR0IF, INT0IF, RBIF. Readable, writable, they all seem to generally say the same thing, except this last one has an X here. Forget what that denotes. GIE, GIEH, Global Interrupt Enable Bit, when IPEN equals 0. So yeah, I'm bouncing around. I didn't know what IPEN stands for, so I just did a separate search. It shows up on page 87. Bit 7 is the IPEN ARCON Register. It's the interrupt priority enable bit. Number 1 equals enable priority levels on interrupts. 0 disable priority levels on interrupts. So this is bit 7 in the ARCON register. So what's the ARCON register? It's the reset control ARCON register. The reset control ARCON register contains flag bits to allow differentiation between resets. The reset control register has 7 bits. And I can remember looking at the table of contents, and like a lot of the beginning sections of the reference manual deals with reset conditions. So it's its own section. But even the oscillator section, I recall, deals a lot with resets and things. But anyway, what's this IPN thing? Because this GIE, GIH bit seems to rely on the IPN along with this next bit. So I'm still not clear on what that is. Hold on. I'll just say it again. Why not? So section 3 deals with reset conditions. And then section 3 shows the ARCON register bits and positions. And the IPN shows up as bit 7. This is on page 82. But then the next instance shows the ARCON register. Is that the same register it's talking about here? ARCON register bits. Is this the same? Looks like the same register. So we're really talking about the same thing. Reto pid por bor. Yeah, it's the same thing. So it just shows this ARCON register again. And what's the ARCON register? It contains flag bits to allow differentiation between resets. So the ARCON is the reset control. So this in section 3 is like kind of the main control register that deals with resets. And I guess we could study each of them, but once again, the IPEN is the interrupt priority enable bit. And setting that to a 1 or 0 can affect the interrupt priority. I would go so far as to say this actually enables interrupts or it disables them. Am I wrong about that? I have to ask a question. I don't really know. So this GIE, the global interrupt enable bit, and the peripheral interrupt enable bit rely on IPN. I'll just read this in. So this is going back to section 3 on resets. And it has a note here. When the wake up is due to an interrupt and the GIH or GIEL bits are set, the program counter is loaded with the interrupt vector 08H or 0s18H. So the GIE, the global, what was that called? Global interrupt enable bit, that's a pretty significant thing relating to resets. And when I search for it, it seems to show up dashed with the global interrupt enable low. Here it is again here, the GIE low. I guess I already covered this in what I read, talking about the global interrupt and the peripheral interrupt being some type of pair. Here it is again, paired together. Peripheral interrupt enable bit. When IPN equals 0. And when IPN equals 1. And here it is here in the INTCON register. You've got the GIE, GIEH, which is the global interrupt enable bit. And I guess the high one. And then you've got the peripheral interrupt enable bit in pair with the GEIL. Anyway, Now we're talking about the timer TMR0 overflow interrupt enable bit. The external, wonder if that's supposed to be internal. int0 internal or external interrupt enable bit. RBIE RB port change interrupt enable bit. TMR0 overflow interrupt flag bit. Timer 0, this is an I, interrupt flag. int0 external interrupt flag bit. RBIF is the RB port change interrupt flag bit. At least one of the RB7, RB4 pins change state must be cleared in software. None of the RB7, RB4 pins have changed state. Sorry, I skipped reading all this stuff. Okay, so this X denotes when a bit is unknown. So all these bits were readable, writable, but I guess the RBIF, which is the port change interrupt flag bit, will be unknown. 0 denotes a bit is cleared. So these are readable, writable, but they're typically cleared. And then this one is unknown. Let's read this. Note, interrupt flag bits are set when an interrupt condition occurs, regardless of the state of its corresponding enable bit or the global enable bit. User software should ensure the appropriate interrupt flag bits are clear prior to enabling an interrupt. This feature allows for software polling. Moving on. Page 182 of the PDF. INTCON Register. The RibPoo, INTED-GO, INTED-G1, INTED-G2, Timer O, IP, RBIP. So the bit 7 is RBPoo, port B pull up enable bit, INTED G0, INTED G0 is the external interrupt 0. Still wondering if that should be internal, but anyway. Well, maybe it's just int as an interrupt. External interrupt 0, edge select bit. Number 1 equals interrupt on rising edge. Number 0 equals interrupt on falling edge. INTED G1, external interrupt edge select bit. INTED G2, external interrupt edge select bit. Unimplemented. TMR0 IP. TMR0 overflow interrupt priority bit. TMR0 overflow interrupt is a high priority event. Bit 1 unimplemented. The RBIP, RB port change interrupt priority bit. RB port change interrupt is a high priority event or a low priority event. I don't know if I read this already. It's the same thing. Interrupt flag bits are set when interrupt conditions occur. Yeah, something about polling. I read that before. INTCON Register. int2IP, external interrupt priority bit. This might be very similar to the above. INTCON Register. And what was this? INTCON just 0 register. So I don't know if these are significantly different. They have a different set of bits. So I'll read the intro part. External interrupt priority bit. External interrupt priority bit. It's got 2 and 1. This is unimplemented. External interrupt enable bit. It's got another one of those. Unimplemented. External interrupt flag bit. External interrupt flag bit. Similar type of note. The PIR register. Depending on the number of peripheral interrupt sources, there may be multiple peripheral interrupt enable registers, such as PI1 and PI2. These registers contain the individual enable bits for the peripheral interrupts. These registers will be generically referred to as PI. Note, if the device has a PI register and IPN equals 0, the PIE bit must be set to enable any of the peripheral interrupts. Although the PI register bits have a general bit location with each register, future devices may not have consistent placement. Bit location inconsistencies will not be a problem if you use the supplied microchip include files for the symbolic use of these bits. This will allow the assembler/compiler to automatically take care of the placement of these bits by specifying the correct register number and bit name. Register 10.4 PI peripheral interrupt enable registers. Timer 1 IE overflow interrupt enable bit. Here you've got the timer 2 IE match interrupt enable bit, overflow interrupt enable bit, TMR3 IE, CCP X IE, capture compare X interrupt enable bit, the ECP X IE enhanced CCPX interrupt enable bit, SS PI synchronous serial port interrupt enable bit, MSS PI master synchronous serial port interrupt enable bit, RCIE USART receive interrupt enable bit, TXIE USART transmit interrupt enable bit, IRXIE CAN invalid received message interrupt enable bit, WAKey CAN bus activity wake up interrupt enable bit, URI CAN bus error interrupt enable bit, TXB2IE CAN transmit buffer 2 interrupt enable bit, TXB1IE CAN transmit buffer 1 interrupt enable bit, TXB0IE CAN transmit buffer 0 interrupt enable bit, RXB1IE CAN receive buffer 1 interrupt enable bit, RXB0IE receive buffer 0 interrupt enable bit, AD analog to digital converter interrupt enable bit, PSPIE parallel slave port read write interrupt enable bit, EEIE EE write complete interrupt enable bit, CMIE comparator interrupt enable bit, BCLIE bus collision interrupt enable bit, LV die low voltage detect interrupt enable bit. The bit position of the enable bits is device dependent. Please refer to the device datasheet for bit placement. Okay, next is PIR registers. Depending on the number of peripheral interrupt sources, there may be multiple peripheral interrupt flag registers, PIR1, PIR2. These registers contain the individual flag bits for the peripheral interrupts. These registers will be generically referred to as PIR. Note 1. Interrupt flag bits are set when an interrupt condition occurs, regardless of the state of its corresponding enable bit or the global enable bit GIE INTCON 7. User software should ensure the appropriate interrupt flag bits are cleared prior to enabling an interrupt and after servicing that interrupt. Although the PIR bits have a general bit location within each register, future devices may not have consistent placement. It is recommended that you use the supplied microchip include files for the symbolic use of these bits. This will allow the assembler/compiler to automatically take care of the placement of these bits within the specified register. Moving down, now we're on page 187. These are the Register 10.5 PIR Register. So this is a register, and it's got a note 1. I think I read a note 1 already. That was this one. Interrupt flag bits are set when an interrupt condition occurs, regardless of the state of its corresponding enable bit or the global enable bit. And that was GIE INTCON 7. So this is a register, and it says note 1. Timer 1, overflow interrupt flag bit. Timer 2 to PR2, match interrupt flag bit. Timer 3, overflow interrupt flag bit. CCP-XIF, CCP-X interrupt flag bit. Capture mode, compare mode, PWM mode, unused in this mode. ECCP-XIF, enhanced CCP-X interrupt flag bits, capture mode, compare mode. PWM mode, unused in this mode. IRXIF, CAN invalid received message interrupt flag bit. WakeIf, CAN bus activity wake up interrupt flag bit. ERIF, CAN bus error interrupt flag bit. TXB2IF, CAN transmit buffer 2 interrupt flag bit. TXB1IF, CAN transmit buffer 1 interrupt flag bit. TXB0IF, CAN transmit buffer 0 interrupt flag bit. RXB1IF, CAN receive buffer 1 interrupt flag bit. RXB0IF, CAN receive buffer 0 interrupt flag bit. SSPIF, synchronous serial port interrupt flag bit. MSSPIF, master synchronous serial port interrupt flag bit. RCIF, USART receive interrupt flag bit. TXIF, USART transmit interrupt flag bit. ADIF, analog to digital converter interrupt flag bit. PSPIF, parallel slave port read-write interrupt flag bit. EEIF, EE-write complete interrupt flag bit. Comparator interrupt flag bit. BCLIF, bus collision interrupt flag bit. LVDIF, low voltage detect interrupt flag bit. Note 1. The bit position of the enable bits is device dependent. Please refer to the device data sheet for bit placement. This, I don't like the word, but esoteric. This must be very esoteric information. Because I'll tell you something. When I look up YouTube videos on people programming PIC-18F chips, first of all, 95% of the videos are people blinking an LED on and off. That seems to be all most people can achieve. Never mind even understanding what all these different bits in registers do. Somehow I continue trying to understand all this. IPR Register. Depending on the number of peripheral interrupt sources, there may be multiple peripheral interrupt priority registers, such as IPR1 and IPR2. These registers contain the individual priority bits for the peripheral interrupts. These registers will be generically referred to as IPR. If the device has an IPR register, and IPN equals 0, the PIE bit must be set to enable any of these peripheral interrupts. The IP bit specifies the priority of the peripheral interrupt. Although the IPR register bits have a general bit location with each register, future devices may not have consistent placement. Bit location inconsistencies will not be a problem if you use the supplied microchip include files for the symbolic use of these bits. This will allow the assembler/compiler to automatically take care of the placement of these bits by specifying the correct register and bit name. Register 10.6 IPR Peripheral Interrupt Priority Register. TMR1 IP Overflow Interrupt Priority Bit. Timer 2 to PR2 Match Interrupt Priority Bit. Timer 3 Overflow Interrupt Priority Bit. CCP XIP CCPX Interrupt Priority Bit. ECCPXIP Enhanced CCPX Interrupt Priority Bit. Where am I here? ECCPXIP Enhanced CCPX Interrupt Priority Bit. MSS PIP Master Synchronous Serial Port Interrupt Priority Bit. SS PIP Synchronous Serial Port Interrupt Priority Bit. RSIP USART Receive Interrupt Priority Bit. TXIP USART Transmit Interrupt Priority Bit. ADIP Analog Digital Converter Interrupt Priority Bit. PS PIP Parallel Slave Port Read Write Interrupt Priority Bit. IRXIP CAN Invalid Received Message Interrupt Priority Bit. WakeUp CAN Bus Activity Wake Up Interrupt Priority Bit. RIP CAN Bus Error Interrupt Priority Bit. TXB2IP CAN Transmit Buffer 2 Interrupt Priority Bit. And here's number 1, here's number 0. RXB1IP CAN Receive Buffer 1 Interrupt Priority Bit. Here's number 0. EEIP EE Write Complete Interrupt Priority Bit. CMIP Comparator Interrupt Priority Bit. BCLIP Bus Collision Interrupt Priority Bit. LVDIP Low Voltage Detect Interrupt Priority Bit. The bit position of the priority bits is device dependent. Please refer to the device datasheet for bit placement. And now we're talking about the ARCON Register, which I think showed up in section 3 on resets. Reto P Bor Por Bor. Yeah, this is the same thing with IPN and Lawword as the first 2 bits. So I remember this. So this seems to have come up in the manual already. The ARCON Register. The ARCON Register contains the bit that is used to enable prioritized interrupts, IPN, as well as status bits to indicate the cause of a device reset. If the device was in sleep mode and if long writes to internal memory are enabled. Well, let's read it again. IPN is the interrupt priority enable bit. Enable priority levels high and low on interrupts. Disable priority levels, all peripherals are high on interrupts. PIC 16C blah 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 compatibility. This causes the interrupt priority IP bits to be ignored. The Lawword long write enable. For details of bit operation, see description of ARCON Register bit in Register 3.2. Unimplemented RI reset instruction flag bit. For details of bit operation, see description of ARCON Register bit in Register 3.2. Bit 3 is the TO watchdog timeout flag bit. PD is the power down detection flag bits. POR is the power on reset status bit. And BOR is the brownout reset status bit. Okay, page 193 of the PDF. Interrupt handling operation. The interrupts are controlled and monitored using several special function registers. These may include the following register types: INTCON registers, PIR registers, PI registers, IPR registers. The PIR registers contain the interrupt flag bits. The PI registers contain the enable bits, and the IPR registers contain the priority bits. The number of PIR, PI, and IPR registers depends on the number of interrupt sources on the device. Interrupt priority. Each interrupt can be assigned a priority level by clearing or setting the corresponding interrupt priority bit. The priority bits are located in the interrupt priority registers: IPR1, IPR2, 3, INTCON2, and 3. 1 in the priority register assigns high priority to the corresponding interrupt. 0 in the register assigns low priority to the interrupt. All interrupt priority bits are reset to 1, meaning that all interrupts are assigned high priority at reset. The IPN bit in the ARCON register enables priority levels for interrupts. If clear, all priorities are set to high. High priority interrupts. A global interrupt enable bit, GIE/GIEH INTCON 7, enables, if set, all unmasked interrupts or disables, if clear, all interrupts. When bit GIE/GIEH is enabled and an interrupts flag bit and enable bit are set while the priority is high, the interrupt will vector immediately. Individual interrupts can be disabled through their corresponding enable bits in various registers. Individual interrupt flag bits are set regardless of the status of the GIE/GIEH bit. The GIE/GIEH bit is cleared on reset when a high priority interrupt is responded to. The GIE/GIEH bit is automatically cleared to disable any further interrupts. The return address is pushed onto the stack and the program counter is loaded with 00, a bunch of zeros, 8H. Once in the interrupt service routine, the source of the interrupt can be determined by polling the interrupt flag bits. The interrupt flag bits must be cleared before re-enabling interrupts to avoid recursive interrupts. Most flag bits are required to be cleared by the application software. There are some flag bits that are automatically cleared by the hardware. The return from interrupt instruction, retfee, exits the interrupt routine and sets the GIE/GIEH bit, which enables high priority interrupts. Low priority interrupts. Low priority interrupts are defined by having a 0 in an interrupt priority register, IPRX. To enable low priority interrupts, the IPN bit must be set. When the IPN is set, PEIE/GIEL bit INTCON 6 is no longer used to enable peripheral interrupts. Its new function is to globally enable and disable low priority interrupts only when the service routine for a low priority interrupt is vectored to the PEIE/GIEL bit is automatically cleared in hardware to disable any further low priority interrupts. The return address is pushed onto the stack and the program counter is loaded with the bunch of zeros 18H instead of the zeros 8H. All low priority interrupts will vector to zeros 18H. Once in the interrupt service routine, the sources of the low priority interrupt can be determined by polling the low priority interrupt flag bits. The interrupt flag bits must be cleared before re-enabling interrupts to avoid recursive interrupts. Most flag bits are required to be cleared by the application software. There are some flag bits that are automatically cleared by the hardware. The retfee instruction will reset the PEIE/GIEL bit on return from low priority interrupts. The GIE/GIEH bits function has not changed in that it still enables/disables all interrupts. However, it is only cleared by hardware when servicing a high priority interrupt. Page 194. High priority interrupts interrupting a low priority ISR. If a high priority interrupt flag and enable bits are set while servicing a low priority interrupt, the high priority interrupt will cause the low priority ISR to be interrupted regardless of the state of the PEIE/GIEL bit, because it is used to disable/enable low priority interrupts only. The GIE/GIEH bit is cleared by hardware to disable any further high and low priority interrupts. The return address is pushed onto the stack and the program counter is loaded with bunch of zeros 8H, the high priority interrupt vector. Once in the interrupt service routine, the source of the high priority interrupt can be determined by polling the interrupt flag bits. The interrupt flag bits must be cleared in software before re-enabling interrupts to avoid recursive interrupts. Figure 10.4 shows a high priority interrupt interrupting a low priority ISR. Figure 10.5 shows a high priority FSR with a low priority interrupt pending. Note, the GIEH bit, when cleared, will disable all interrupts regardless of priority. So here's the oscillator doing its oscillation, going up and down, and I guess every 4 oscillations is 1 clock cycle. Here's the clock out. Int 0 is a high priority interrupt, and it occurs after 1, 2, 3, 4, 5 clock cycles. Okay. Int OIF is high priority. So just presumably because this high priority interrupt occurs here, then on the next clock cycle, this int 0IF high priority goes high. Okay. then the GIE/GIEH bit is high till a few clock cycles after this happens, and it goes low. Don't know what that's doing. INT2 pin on the first clock cycle has a little blip going high, and because of that, on the next clock cycle, INT2IF low priority goes high on the next clock cycle and seems to stay there. PIE/GIEL is high for 3 clock cycles, and I guess it's reacting to this and this. So then for a couple more clock cycles it stays high and then goes low, and then goes low, and then the high priority thing happens. Vector to high priority ISR, and it's just showing the program counter what it's doing. Program counter instruction fetched. Program counter plus 2, program counter plus 2, then it shows the 0018H register location, 001AH, 001CH, 001CH, 008H, high priority, vector to high priority ISR, 000AH, 000CH. So I'll read this in a second. Just to reaffirm what I'm even reading here, figure 10.4, a low priority ISR interrupted by a high priority interrupt. So here's a low priority interrupt, and then a high priority interrupt interrupts that. Instructions fetched, instruction program counter, instruction program counter plus 2. Yeah, I won't read all that. Kind of covered it here. Getting it a little bit. Am I going to read all this? No, I don't think so. High priority interrupt with low pending low priority. So here's the high priority happening. Then the low priority interrupt happens. And I guess this is where the magic happens. The PIE/GIEL, the high or vector to high priority interrupt, return from high priority interrupt vector to low priority interrupt. If you don't understand it, you'll have to pause and study the screen. Okay, now moving forward. Figure 10.6 and figure 10.7 shows two cases where a low priority interrupt has occurred and then a high priority interrupt occurs before the low priority ISR can begin execution. Figure 10.8 shows the first instruction of the low priority interrupt at address 18H beginning execution when the high priority interrupt causes the program counter to be forced to the high priority interrupt vector address 08H. So in the first chart it shows a low interrupt with high interrupt within one cycle. So it happens, what was this? Is this the... Okay, so I'm looking at the previous chart. This INT0IF, whatever this one is, this is the high priority, right? So you've got the low priority having an interrupt within the first cycle. The very next cycle, you get a high priority interrupt. So it begins a vector to low priority interrupt, but then it vectors to high priority interrupt. Return from high priority interrupt to low priority ISR. So maybe it just shows how it goes from low priority interrupt to high priority interrupt, but then maybe this wasn't taken care of, so maybe it goes back to the low priority interrupt service routine. Is that what that stands for? Okay, so now I just searched it in the manual, page 134. Oh, maybe I should have read this section. Well, it's talking about section 7 is the memory. So if I really want to completely solidify my learning on interrupts, go back and watch some of the videos I created on the memory section. Not even sure I read that correctly originally. But it's talking about the interrupt stuff here. And yeah, ISR, interrupt service routine. Everything always tends to go back to this section of the manual. So anyway, I won't read the whole chart, but here's the ret fee instruction. Low interrupt with high interrupt within 2 cycles. So this one was within 1 cycle, and it kind of shows what happens within 2 cycles. Vector to low priority interrupt to high priority interrupt, then it goes back to an interrupt low priority ISR. I guess that really has to be studied as to what's going on there. Low interrupt with high interrupt within 3 cycles. So now I'm on page 197. Low priority interrupts interrupting a high priority ISR. A low priority interrupt cannot interrupt a high priority interrupt service routine. The low priority interrupt will be served after all high priority interrupts have been served. Simultaneous high and low priority interrupts. If a high priority interrupt and a low priority interrupt are sampled at the same time, the high priority interrupt service routine is always serviced first. The GIE/GIEH bit is cleared by the hardware and the device vectors to location 8H to the high priority ISR. After the interrupt is serviced, the corresponding interrupt flag should be cleared to avoid a recursive interrupt. The ret fee instruction resets the GIE/GIEH bit, and if no other high priority interrupts are pending, the low priority interrupt is serviced. Fast context saving during high priority interrupts. A fast interrupt service option is available for high priority interrupts. This is done by creating shadow registers for a few key registers: WREG, BSR, and status. Shadow registers are provided for the status, WREG, and BSR registers and are only 1 deep. The shadow registers are not readable and are loaded with the current value of their corresponding register when the processor vectors for a high priority interrupt. The values of the shadow registers are then loaded back into the actual register if the fast return instruction retfee 0x01 is used to return from the interrupt. An example for fast context saving is shown in example 10.1. Here it is here. Fast context saving. Org 0x08 interrupt service routine code WREG BSR and status need to be saved upon entering the high priority interrupt service routine. retfee 0x01 WREG BSR and status will be restored. Note, fast interrupt saving cannot be used reliably if high and low priority interrupts are enabled. See section 10.3.1.7. Context saving during low priority interrupts. Low priority interrupts may use the shadow registers. Any interrupt pushes values into the shadow registers. If both low and high priority interrupts are enabled, the shadow registers cannot be used reliably for low priority interrupts, as a high priority interrupt event will overwrite the shadow registers. Users must save the key registers in software during a low priority interrupt. For example, store the status, WREG, and BSR registers on a software stack. Execute the ISR code, restore the status, WREG, and BSR registers from the software stack. Moving down, section 10, still on the same section. Example 10.2 shows example service routine code for when high and low priority interrupts are enabled. This almost is more understandable. Anyway, I guess I should read it. Interrupt service routine template, org 0x08, high priority interrupt service routine. Push _ reg _ h, seems like just the label they gave it. Move f, wreg _ temp _ high, move ff, bsr temp high, move ff, status temp high, high priority interrupt service routine, ISR, code goes here, pop reg h, move ff, bsr temp high, bsr, move f, wreg temp high, w, move ff, status temp high, status, retfee 0x00, push reg l, org 0x18, low priority ISR, move wf, wreg temp low, move ff, bsr temp low, move ff, status temp low, low priority interrupt service routine, ISR, code goes here, pop reg l, move ff, bsr temp low, bsr, move f, wreg temp low, move ff, status temp low, status, retfee 0x00. Moving down, interrupt latency. On page 200 here, getting close to the end. I'm going to try to gloss over this stuff. Interrupt latency, 10.3.1.8. For external interrupt events, such as the RB0/int0 pin or port B change interrupt, the interrupt latency will be 3 or 4 instruction cycles. The exact latency depends when the interrupt event occurs. The interrupt latency is the same for 1 or 2 cycle instructions. Interrupt latency for 1 cycle instructions. Figure 10.9 shows the timing when an external interrupt is asserted during a 1 cycle instruction. The interrupt is sampled on Q4. The interrupt is then acknowledged on the Q2 cycle of the following instruction cycle when the instruction program counter is executed. This is followed by a forced NOP dummy cycle, and the contents of the PC are stored on the stack during the Q3 cycle of this machine cycle. By the Q3/Q4 boundary of instruction cycle 2, the interrupt vector is placed into the PC and is presented on the program memory bus on the following cycle. This cycle is also a dummy cycle executing a forced NOP, FNOP, so that the CPU can fetch the first instruction from the interrupt service routine. So there's the program counter, instruction fetched, instruction executed, int xif flag, GIE/GIEH bit, stack RAM register. Stop and study. Pause and study. Moving down. Section 10. Interrupts. 10.3.1.8.2. Interrupt latency for 2-cycle instructions. Figure 10.10 shows the timing when an external interrupt is asserted during a 2-cycle instruction. The interrupt is sampled on Q4. The interrupt is then acknowledged on the Q1 of the following instruction cycle when instruction PC is executed. This is followed by the second cycle of the instruction, and the contents of the PC are stored on the stack during Q3 of this machine cycle. For all 2-cycle instructions, the PC may be updated with a new PC value to execution control instructions like go to and call. The reason for the forced NOP dummy cycle is to maintain consistent interrupt latency between one of the 2-cycle instructions. 2-cycle instructions require this cycle for the update of the PC to a new PC value, because all 2-cycle instructions, with the exception of MOVEFF and MOVELF, what's that instruction, are execution control type instructions that update the PC with a new value, i.e. go to and call. The MOVEFF and MOVELF instruction will increment the PC by 2 in this cycle because an operand fetch takes place in the second cycle. By Q3/Q4, the interrupt vector 08H is placed into the PC and is presented on the program memory bus on the following cycle. This cycle is a dummy cycle executing a forced NOP, FNOP, so that the CPU can fetch the first instruction from the interrupt service routine. Note, when using the MOVEFF instruction with any one of the PCL, TOSU, TOSH, and TOSL registers as destination, all interrupts have to be disabled. And pause and have a good study for yourself. Pause it. So now, moving down here, page 202, interrupts during table write operations, long writes. The long write is necessary for programming the internal EEPROM. Instruction execution is halted while in a long write cycle. The long write will be terminated by any enabled interrupt. To ensure that the EEPROM location has been well programmed, a minimum programming time is required. Typically, a timer interrupt is used to time and terminate the long write. Having only one interrupt enabled to terminate the long write ensures that no unintended interrupts will prematurely terminate the long write. And you can see the actions happening all in here. And it's got notes on this. INTXIF flag is sampled here. Interrupt latency 3 to 4 TCY, where TCY equals instruction cycle time. Latency is the same whether instruction PC is a single cycle or 2-cycle instruction. That's happening at note number 2. Number 3, clock out is available only in RC oscillator mode. 4, for minimum width of int pulse, referred to AC specs. Note 5, int XIF is enabled to be set anytime during the Q1 cycle. Scrolling down, section 10 interrupts. Example 10.3 enables high and low priority interrupts. The priority level for the peripherals is loaded into the IPR register, ERP1 value, and the peripherals that are enabled depend on the value of the PI1 value, which is loaded into the PI1 register. Yeah, pause and have a study. Well, it's almost worth reading. Move LW, ARCON value equals 1 question marks. Move F, ARCON. Move a literal value to the working register, IPR1 underscore value. Peripherals with high priority have a 1 in their bit position. Those with a low priority have a 0 in their bit position. Move WF, ERP1. Clear F, PIR1. Clear all flag bits. Move a literal value to the working register, PI1 underscore value. Enable desired peripheral interrupts by setting their bit position. Disable others by clearing their bit position. Move WF, PI1, clear F, INTCON 3, clear F, INTCON 2. Move LW, 0xC0. Enable high and low global interrupts. Move WF, INTCON. Scrolling down. Design tips. My code does not seem to execute properly. Answer 1. There are many possible reasons. A couple possibilities related to interrupts are: interrupts are not enabled, so the code cannot execute your expected ISR. The interrupt may not be set to the high priority level where your ISR code is located. Scrolling down. Section 10 interrupts. Related application notes. And this doesn't say anything. Scrolling down, revisions. And next section, so covered everything. Do I want to look for other examples of interrupts? Maybe not. That's going to bring me back to the section 7 on the memory, because the interrupts show up there a lot. Just a note to self to maybe rewatch the memory section 7 video. I don't know, did I make a video on that? Maybe I have to. Alrighty, so section 11 is talking about the I/O ports. That's worth a read. And it starts talking about how the peripherals are multiplexed. So there's a lot of instances of interrupts on each pin. This is a neat section because it starts describing the multiple uses of the different GPIO pins. It's just interesting to read. So I suppose it's fair to conclude that interrupts really show up all over the manual, particularly in section 3 on the device reset conditions, section 7, which is the memory section. But I just wanted to satisfy my interest to know where else it shows up. Here's section 12, parallel slave ports, showing some interrupt. In section 12 of the manual, it's only covered half of the instances of interrupts. So maybe I'll leave it at that. That should be a pretty good grounding of interrupts.